going to hear from three exciting speakers, and let's get started right away. First, we'll hear from Sabine Susstrunk, who is a professor at EPFL, and who's going to talk about neural cellular automata for self-organizing textures.
Well, thank you very much for the introduction. Good morning, everyone. So, to get a line from Monty Python, so now for something completely different than what we heard before, namely about neural cellular automata. Yishgar and Yitao Xu, and my postdoc, Tong Zhang. Let me start with contrasting two different types of systems that we can find around us. So the first system is all the stuff we humans have engineered. We spent numerous hours on planning or designing such systems and anticipating every failure mode. If something goes wrong, the whole or part of the system breaks down, and there is no capacity for the system in itself to recover and fix itself. We need human experts to fix it, if it's even possible to repair it. It would be kind of unreasonable for the toaster to think about fixing itself, or maybe in its community for a SPAD camera to fix itself. However, there are other types of systems created through natural evolutions who are capable of actually fixing themselves. Think about the human brain. If you had a stroke or a concussion, you have some rewiring going on, and the system can actually get back and does the function that it was supposed to do. It can also self-organize. Think about all those flocks of birds who have thousands of birds who basically go somewhere, land somewhere, and they don't necessarily have a leader. They actually self-organize. And then we have morphogenesis, where you have a development of one single cell or one single organism that actually then evolves into a very complex system. So exactly what makes these living systems so different from the engineered system that we built? Well, looking at these living natural systems, we see endless variations and different underlying mechanisms. So nature is full of complex and beautiful patterns. And these patterns are the result of an underlying complex self-organizing system that can exhibit emergence. Emergence in a general sense describes the phenomenon where complex systems or entities exhibit properties or behaviors that are not present in their individual component, but arise from the interaction of those components. So in other words, it is essentially about how simplicity can give rise to complexity and how systems become more than the sum of their parts. Now, we were interested to actually think about this and say, well, wouldn't it be nice if we can take inspiration from these natural systems and inject them into our engineered systems? Now, one of those examples of such a system is the cellular automata. And I'm going to explain the cellular automata by taking the example of Conway's game of life, which is a very simple automata. It is insofar a complex system that we have many identical cells that each follow simple rules. It has self-organization. All of these cells follow the same rules and are not different, yet when we let them act together, they can self-organize and create interesting patterns, such as gliders or spaceships. And you can think of the pixels as being the atoms and the patterns that emerge as being molecules or cells. So this is an interesting video that you can actually find online. And in case I'm going to try to, if I can find my mouse, oops, it's over there. Let me speed this up a little bit. And zoom out. And I think you can start seeing that macroscopic patterns arise up to the end, where you can see some repetition of the micros pattern on a macroscopic scale. So this you can find online and play it in the whole length of about 2 minutes. I just basically sped it up for this presentation. So what is a CA, or cellular automata? It is composed of cells, as I mentioned before, and a cell is identified by its position and state at each given time step. The cell has a neighborhood, and this neighborhood is considered in the perception stage when the cells perceive their environment, resulting in a perception vector. During adaptation, each cell updates its states according to its perception vector, resulting in the updated cell state. In the case of Conway's game of life, the cells are binary, so either on or off. The perception is a simple convolution kernel, and the adaptation a simple non-linear function. And now 6 minutes of my talk is over, and I've taken you to the 1970s. Conway's Game of Life goes back to the 1970s. So it took 50 years, and like everything in our community, we basically went, oops, sorry, this was the wrong way. We went neural. So Alexander Motvintsev and his colleagues in 2020 basically presented the architecture for a neural cellular automata. Now you might remember Alexander Motvintsev from Deep Dreams. He was the Deep Dream person about a decade ago who illustrated what is actually happening in the CNN. So, in neural cellular automata, the cell states are more sophisticated and have actually many channels. The first 3 channels are the RGB color. The perception stage is comprised of 4 convolutional filters, and these filters are not trained and are actually very common. So it's the identity filter, it's the Sobel X direction, Y direction, and a Laplacian. And the adaptation stage is a neural network. It's actually a 2-layer MLP. So during NCA training, we apply the NCA updates many times, and then evaluate an appearance loss function and train using backpropagation. And the results look about as this one. Here are some results. You can observe the cell state updates, and you can see the patterns emerging. But what you can also see is an emerging dynamics of these patterns, even though it was only trained on a static sample, as you can see below. So what are our contributions to this neural cellular automata world? We made several contributions, and I'd like to briefly present them. So in our DY NCA, we adapted the NCA model so the emergent dynamics can be controlled. In the noise NCA, we learned to control the temporal and spatial scale of the NCA pattern. And in mesh NCA, we generalized to 3D meshes. All of these papers actually have interactive demos, so you see the link on top, and you can encourage you to play with them if you are interested. So as I mentioned in dynamic NCA, our goal was to make the patterns move in a structured way. So during training, we actually added, besides the appearance loss, also a motion loss. And the motion loss can be a vector field or a short video. We quantify the motion using a pre-trained optic flow prediction model. And we also changed the architecture in 2 ways to make it suitable for synthesizing dynamic textures. So first, we introduced multi-scale perception to improve the quality of the results, especially for higher resolution. And we also add positional encoding to generate different behavior or motion based on the position of the pixel. So here is a video of the demo you can find on our website. So you can have different textures and motions. Keep in mind, for each texture, we have to actually train 1 NCA. But training is about in the order of 20 minutes on 1 GPU. So it's a very lightweight training. So we can also have a brush tool where we basically, here you can see that it can organize itself, and then we have also different local senses of direction, so you can have more fancy motion patterns if you want. We can also do dynamic style transfer because the motion and the appearance does not have to come from the same samples. In the noise NCA paper, we studied how to make the NCA continuous in time and in space. You know, recall that before they were trained using discrete, grid, and time steps. I'll skip the details, you know, just giving you a hint. There's all about differential equations, and go directly to the results. Because with the space and time continuity, we can really put multi-scale patterns on a single grid and create special effects. So what you can see here, if you look closely, you can also infer actually this depth illusion, right? This is actually a scale, but because of the different kind of because of the different sizes of the different patterns, it does create a depth illusion. Then we can also, of course, vary the scales over time. And we find really also interesting emerging NCA behaviors like the bubbles. If you look at them when they enlarge and when they basically split off from each other. Then we also generalize the NCA frameworks to 3D. You know, in 2D we have a well-defined grid structures, and in 3D we actually generalize it to 3D meshes. And the perception stage changes accordingly, of course. We go from a grid to a mesh perception, and we have to adapt the convolutions accordingly. Sorry. So the key insights in changing the convolution is that we're now not treating the convolutions anymore as as regular convolutions on a grid, but as polar functions that return the filter weight as a function of distance and angle between the pixels. This is then easy to generalize to non-grid structures, and in 3D, this can be expressed as spherical harmonics. So for mesh NCA training, everything other than the perception part remains the same. So we are updating it. The mesh NCA iteratively updates the cell states according to the update rule. The vertex attributes such as color and other surface properties are extracted from different channels of the final state of ST. They are then fed into a differentiable renderer to get the output image, which is evaluated against the target texture to compute the loss. So we can train the mesh NCA with a target texture given an image, like here, or a text, or a desired motion. And of course, the system is fully differentiable so that the loss can be used to perform back propagation for the training. So during training, mesh NCA only uses the icosphere mesh, but we can generalize to different meshes, as I'll show you in a minute. So here are the results of image-guided and text-guided synthesis. After training, the mesh NCA can synthesize textures also with natural motion, although the targets are static images. And then moreover here, what you can see it, if it's straight with additional motion targets, the mesh NCA can synthesize desired dynamics. So this mesh NCA has really several interesting test time properties. Again, we only train on the icosphere, but it can generalize to unseen meshes without retraining. Even if the mesh itself is moving, our model can still synthesize desired textures without diverging. We can change the mesh structure by subdividing it, which changes the texture density accordingly. So during training, our model uses fixed spherical harmonics. We can change them during testing through rotation, which in turn controls the orientation of the patterns in real time. And the same mechanism can also be applied to motion-guided models and change the motion as desired. For example, here the converging motion can completely turn around when the rotation is 180 degrees. We can also disturb it. It self-repairs itself, as I showed you before. And then a really interesting concept is grafting, where we can make some cells follow one rule and the others follow a second rule. And in this scenario, too, the two mesh NCAs actually cooperate to generate a hybrid texture. And we kind of designed a brush to implement this. So what is next? So our current work right now is actually extending the relatively limited resolution that we have to the infinite resolution. And here's some examples that we have on our website that you can see. We can do it for 2D, 3D meshes, but also for morphogenesis. And here is an example that shows you the morphogenesis application of the NCA. So, thank you for listening. I took my photo off. So, so again, this is really the work of these three absolutely wonderful collaborators. We have Alexander and Eric Nicholson, Ali, Alexander, and Wenzel Jakob with the cells to pixel work. You have all the websites if you want to play with the demos. But I do want to make a point. So this is all kind of fun and cute and visual and can be used for many, many, applications, but that's not it, right? We've actually used this concept of NCA in a totally different kind of work where we made transformers more robust to adversarial attacks. So this has nothing to do with kind of a visual task, but something of actually making them more robust because they're self-repairing. And so there's lots of kind of, for us this is the beginning of a research area that go in totally different directions. But this concept of this simple kind of system that could actually help a more complex system is, I think, something very powerful to explore. Thank you for your attention.
Thank you, Sabine, for the fascinating visuals and the talk. We have time for a few questions.
Hello. It was a great talk. I really loved the visuals. I was going to actually ask, about the you hinted at this direction of making things more robust with cellular automata. Is this something that have you ever, sorry, I need to figure out how to word the question. Have you thought of this in sort of a compression context of like, if I have a giant image that I know is made of really compressible textures, can I throw some compact automata at it, and then I get my 45 megapixel gecko in not 45 megapixels?
Yeah, exactly. Yes, to a certain point, this is what the morphogenesis is kind of all about. But some people, there's a German group who've actually exploited that for medical imaging on edge devices. So this has been, so there are other groups who actually work on this. We personally haven't taken it that far, that specifically yet. But yes, there is absolutely applications also in this kind of, domain of compression.
Hello. Oh yeah. You mentioned the point about having the automata adapt to like attacks, but could you also then have the attacks be automatas that will self-adapt to the adaptation of in response to attack?
You have an evil mind. No, I'm teasing. Yes, of course, right? Yeah, of course. Yeah. I'm trying not to think about all these kind of things we can do to our systems.
I had a question. When you're working with meshes, does the topology and how bad I can make the topology actually matter? I can take the very same shape and I can make it have a nice mesh with equilateral triangles and everything. Or I can make it the very same shape and have it an extremely bad mesh with long triangles, self-intersections. Like also, I can make it as bad as I want. So does the texture in that case get impacted?
It's a good question. I mean, keep in mind that we're working basically on a neighborhood, right? So if the neighborhood, so we don't specifically care if it's bad in another kind of area, but I've never thought about it because we did not try it on bad meshes. We tried it on the meshes we could get. So hopefully, you know, being self-repairing, it could actually improve, but I cannot give you a real answer to that one.
Thanks for the awesome talk. I'm curious, so you showed that these automata can fit really visual patterns that sort of visually make sense. I'm curious if they could also fit sort of less visual patterns, like maybe the weights of a pre-trained neural network. Could you have some sort of adaptive version where you could maybe replicate the weights through automata?
Yeah, absolutely, right? I mean, this is totally fully differentiable, right? I mean, you can have a loss function against something, whatever you want it to have. So you can train this on any kind of data. It does not have to be visual. No.
All right, so let's thank our speaker again. Our next speaker will be Chowdhury, who is an assistant professor at the University of Texas at Austin, and he will talk about exploring the non-convex landscape of biological inverse scattering.
Okay, thank you all for having me here. I'm so excited. My name is Chowdhury. I'm a assistant professor at the University of Texas at Austin. Everything that I'll be presenting today has been done by my funding sources from CZI and NIH. Okay, so the main lab motivation that we pursue is to develop technologies for computational microscopy towards applications in the basic and biomedical sciences. The specific problem that I'll be talking about today is our lab's effort to achieve some version of deep tissue imaging. To introduce the problem, if you have an object that's within tissue, right, as the object gets deeper and deeper into tissue, light starts scattering due to the heterogeneity of the tissue itself. That scattering effect prevents lenses from being used to tightly focus the light, and this leads to a lot of image blur and a lot of other artifacts. So this is specifically a problem in biology because biology occurs at all size scales. So microscopy is great at when it comes to imaging, like samples that are composed of maybe like thin distributions of cells, but it starts really struggling when you start getting to multicellular organisms or other samples that are maybe like a few hundred microns, and then it really becomes not the right tool for the job when you get above around maybe like a centimeter or so. So our lab's effort is try to figure out how can we use computational methods to try to unscramble these effects of scattering. So in the work that I'll be showing today, we are going to be focusing, let's see, specifically in the depth range of a few hundred microns. So this is the realm within which we have had some success, so those are the results I'll be showing today. So our strategy to combat this or to reverse these scattering effects computationally is to rely on this principle that if you know the refractive index of the sample, then you know the scattering. Specifically, refractive index, if you can compute the refractive index of the sample, you can undo all of the effects of scattering. And the really nice thing about this is that the map of 3D refractive index that you retrieve can itself serve as a volumetric image, a label-free image of the sample's 3D morphology. And so for the rest of our talk, the way we treat this problem is inverse scattering. If you do that successfully, you should get a morphological image of the sample based on refractive index. Okay? Okay. So, okay. This is not unique to us. Refractive index tomography has existed for a few decades at this point. It actually has been traditionally deployed towards samples that are weak scattering. And the reason for that is that if you can make the approximation that the sample is weak scattering, you can linearize the scattering problem. And that allows you to efficiently and analytically invert the scattering problem and reconstruct really nice refractive index. Weakly scattering samples typically mean, again, like monolayer cell distribution. So here's an example. This on the on the left is a wide field image of a set of monolayer cells. You can't see much because these are transparent and pretty thin. If you're able to invert the scattering problem and do refractive index tomography, you start getting something that looks like this. And so if you take a zoom in, you can see that based on refractive index tomography, you can get really nice label-free microcellular submicron resolution imaging contrast based on just the refractive index. So this has actually been wildly successful in many branches of biology that are limited to weakly scattering samples. This is a problem when we go to larger samples like we want to. Specifically, if we go towards, in this example, a C. elegans, which is known to be transparent but is still multiply scattering, is a multicellular organism that's heavily used in basic science for lots of different types of studies. If we use the same weak scattering inverse model to reconstruct this sample, we get something that looks like this. And you can basically see that you can't see any of the internal features. And this is because there's a model mismatch between the weak scattering approximation and the sample itself. So we are interested in driving towards larger multicellular samples. And so for this class of samples, you need to handle multiple scattering. So this is the motivation behind a lot of what we do in the lab. This is also not new to us. In the recent years, many groups have proposed their own different models to combat multiple scattering. I typically like classifying them into 3 groups. They each have their pros and cons. In our lab, all the results that we'll be showing in this talk is based on our multi-slice model that came out a few years ago. And so to show you the capabilities, I'll show you the reconstruction result using that model in comparison to the weak scattering approximation. When we use our model to reconstruct the same sample from the same data, right, we get much higher imaging clarity. You can see the interorganismal features, the pharynx, the mouth, and so on and so forth. And we can actually do this at whole organism scales with the C. elegans. So this is great. But there is a challenge here that will be the focus of this talk. One of the key disadvantages of inverse scattering for multiple scattering phenomenon is that many of these solvers are iterative and specifically non-convex. What that means is that as your samples get larger and more complex, there's a very real possibility of getting stuck in local minima. So what I'm showing here is the reconstruction of an intestinal organoid using the same exact data, same imaging conditions and everything, and all I've done is use different strategies with how I iteratively solve the inverse scattering problem. And what I'm showing you here is that based on simple implementation strategy, nothing different about the physics or the forward model or anything, you can get wildly different results. At the best, one of them is realistic, one of them is correct. At the worst, none of them is correct. But clearly, you can see scenarios where the ones on the far left are obviously incorrect because they don't represent reality well. And this is something that we kept getting again and again and again when we try to extend our work towards extremely scattering samples. And so the subject of this talk is to kind of explore some of the methods that we found to be empirically successful in stabilizing the non-convex landscape when trying to reconstruct these types of scattering samples. So the outline will simply be, I'll quickly describe our multi-slice scattering model, and I'll talk about how we collect data and then show you some imaging results based on the different types of implement strategies that we use. Okay, so let's talk about the scattering model first. So our multi-slice scattering model that we use is, again, not unique to us, but it's a pretty simple way of describing 3D scattering. It's actually approximating volumetric scattering as a layer-by-layer accumulation of 2D scattering events. In this case, we have an electric field that propagates to one layer, gets modulated by the transmission function of that layer, which is itself dependent on the refractive index, and then propagates to the next layer. So that whole layer-by-layer accumulation effect can be really nicely encapsulated by a single recursive equation. And so the last layer, E big sub m, is related to the output of our forward model is related to the last field that is coming out of our sample. That relationship between the forward model's output and that last field is dependent on how we acquire the data. So in the scenario where we captured the data interferometrically, so in this case, little g, or the g operator is the forward model. In the case where we captured the data interferometrically, g is simply the last field that comes out, just the raw complex valued amplitude and phase field. In many scenarios that I'll talk about today, we actually find that it's better to throw away the phase, which is kind of counterintuitive. But in the case where we do amplitude-only detection, such as the case for non-interferometric systems, our G is simply, I'm not sure if you can see that, is simply going to be the amplitude of the last layer electric field. And we find that this has a really large effect on our reconstruction fidelity. Okay, so let me talk about how we collect data. We've built an interferometric system, and essentially, we illuminate the sample, we collect an interferogram. That interferogram can be decomposed using off-axis holography principles into an amplitude and phase component, right? So we have access to both amplitude and phase of the light scattering from the sample. And the key thing that we do is that we illuminate the sample with multiple angles. So we're collecting a data set with angular diversity, right? And the idea is that at each angle, we collect amplitude and phase. So if you want to input complex valued fields into our inverse solver, we use both amplitude and phase. In the case where we only want to do amplitude-only cost function, we just throw away the phase and use only the amplitude. And this allows us to compare both scenarios under the identical experimental conditions. Okay? So to kind of characterize imaging performance, we use a scattering sample. So we have collaborators in Poland who are experts at making scattering phantoms that are customized. And so for this presentation, I'll be showing results from scattering phantoms where you have a cell phantom encased in scattering cubes, 40, 60, 80, and 100 microns. So the larger the sample, the more accumulated scattering you have. This is kind of our way to test our framework across different scattering levels. Okay, so let me show some quick results. On a 40 micron scattering phantom, when we do our inverse scattering to get refractive index, by only using the amplitude component, so we throw away the phase, we only use the amplitude, we get a pretty good 3D reconstruction right here. So not bad, pretty good. And then we compare that to when we do the reconstruction using both amplitude and phase. And we see that we get a pretty terrible reconstruction. This is counterintuitive to us because you would assume that phase has more information, so why doesn't it help your solver? So this actually troubled us for a while. Our speculation is that when you look at the raw fields of these types of phantom, if you use the phase measurement, you are beholden to these phase wrapping artifacts. And remember, the more scattering a sample gets, the more phase wrapping it occurs, right? And so this phase wrapping introduced an ambiguity which we believe screws with the phase information in the solver. Now, so if these are both conducted when we have homogeneous initial guess. So we don't use an initial guess. And we see that with no initial guess, using a complex valued phase cost function gives us worse results. But if we were able to initialize the complex valued cost function using, let's say, the weak scattering approximation that I talked about earlier, we can go back to a pretty good performance. So this is showing the benefits of a warm initial guess, right? Now, let's see if this generalizes across multiple size scales. So we have 60, we have 80, and we have 100. And we see that the trends that I showed with the 40 seem to generalize. In all scenarios, a warm initial guess with a complex valued cost function gives good results. No initial guess with an amplitude-only cost function gives decent results. No initial guess with a complex valued cost function gives terrible results, right? So as of right now, based on just this preliminary data set, our viewpoint is this is the worst implementation strategy in the middle, right? So let's see if this scales up to biology, right? So we did the same experiments on an organoid sample. This is real-world data. This is an organoid where, again, We did complex valued phase, complex valued cost function with no initial guess, amplitude cost function with no initial guess. That looks a lot better as we expected. But here's where we get surprised. We did a complex valued cost function, let me see, even with an initial guess, and we still get these phase wrap artifacts here. And our viewpoint here is that this sample is more scattering. If you look at the phase maps, let's see here. If you look at the phase maps, this sample is more scattering than the phantom. It has more phase disturbance or phase wrapping artifacts. And so that weak scattering approximation is not sufficiently warm at its initial guess. So this kind of leads us to wonder, well, does that mean we just throw away the phase and use amplitude? Amplitude seems to work well, right? It seems to work a lot better, so do we just throw away the phase? Yes and no. What we see here is that even the amplitude-only reconstruction seems to have some artifacts. It's not as pronounced as the complex valued cost, but there are artifacts, like these shadowing artifacts. We see these in other types of modalities as well. And so the question we ask is, how can we use the phase information without putting it directly into the cost function? So our strategy here is to introduce defocus diversity. So remember, we're collecting both phase and amplitude at all illumination angles, which means we can have a data set like that. If we have both phase and amplitude, we can actually computationally, defocus the measurements. So we can computationally introduce defocus as another form of diversity to constrain the problem. And then, once we synthetically generate these defocus measurements, so we're not collecting new measurements, we're just generating these measurements. Once we generate these measurements, we can throw away the phase and then just use amplitude in our reconstruction. So when we do that, we actually get much better reconstructions in this case. So this is, again, complex valued cost, real valued cost without any initial guess on the left, with initial guess on the right, and then intensity-only cost function with no initial guess, but with the refocusing. And so in that case, we see that a lot of these shadowing artifacts are disappearing, have gone away. And so we see this that this seems to be pretty general. We implement this on different types of samples. In this case, I'll show a mutant C. elegans is a gene knockout worm. We compare it to wild type. We see a lot of speckle patterns because it's highly scrambling. It looks almost uncorrelated in a sense. If you were to use conventional multi-scattering inverse solver without this refocusing aspect, we don't perform very well. So here's a phase map just showing how chaotic the phase variations are. When we look at the reconstruction with both refocusing and without focusing, again using only amplitude, we throw away the phase after refocusing, we can see a clear difference between the performance. And so we can actually see that when we take a zoom up, many features in the sample are much more clear if you do the refocusing aspect. So this is our way of stabilizing the problem. We're doing this capability at whole organism scales with the C. elegans, and this is kind of a video of showing our capabilities for volumetric imaging. Our collaborator is really excited because we can see all of the high density lipid structures scattered throughout the worm. So here's a quick fly through. We're actually using this for biology, for basic science aging research, because the lipid organization within the volumetric worm has implications for that. And I'll end with the last slide, which is that we're trying to push this towards larger and thicker samples. And the methods that I showed here are, I'm not going to say that they're complete, but we like to think that they give us a starting point to image a lot of developmental processes that occur within highly scattering tissue, such as embryos, such as different types of developing organisms. And this is an active problem that's in the field, and I know that there are many people who can maybe implement different types of inverse scattering strategies on this problem. And so we're hoping to make this data set open to see if there are drawbacks to our method. Maybe there are other methods that we can use as well to address those. Anyways, with that, thank you very much. Happy to take any questions.
All right, we have time for a couple of questions.
warm start from the single scattering approximation wasn't really cutting it. I'm curious if you've tried using a warm start just from the amplitude-only reconstruction, since that was sort of more stable, but just had these darkening artifacts. Did that help at all?
So you mean using the warm start from the amplitude-only reconstruction and then... No, we have not actually. That's actually a pretty good idea. We should try that.
Okay, we'll talk after.
Yeah, we haven't tried that, yes. That's a great idea.
Hi. I was wondering, you talked about the non-convexity, but after you converge, can the cost function at least differentiate the correct versus the wrong solution? And would phase be useful at least there? Like, does that make sense?
Yeah, sure. There were differences in the converged cost function, that's true. So there were, but we didn't find a pattern between what value the cost function converged towards and whether the reconstruction was realistic or not. I think that question actually deserves a bit more investigation actually. So, but we just haven't, once we found that taking the phase out of the cost function and then using phase indirectly with the defocus measurements, once we found that that kind of stabilized the inverse solver, we kind of just went that route. So we haven't explored that question you asked more in depth.
Can I ask a related question?
Yeah.
So into my non-expert eye, a lot of the examples you showed, sorry, there's no example now, I couldn't really tell which one was the realistic or the real reconstruction and the artifact reconstruction. It seemed very hard to judge whether some of the features we see are actually artifacts or the real biological features. I'm guessing that people that may have training can make that determination more easily or more confidently than I can. But I was curious about your comment. Yeah, here, for example, those what you point with the yellow arrow as a phase artifact, to me, and again, zero training to that, seemed like it may be an actual layer that exists there that we are reconstructing.
So that's a really great question. So the reason I can say that this is an artifact is because we're working hand in hand with our biological collaborators, and this is not realistic in the way organoids are. So organoids, these types of organoids should not have something that looks, there's nothing of biological significance that looks like that. In contrast, if you look here, you don't see that, right? Similarly, if you keep going deeper, you'll see that these wraps become more pronounced, right? But you actually make a very good point, which is that when we're imaging things that we don't already know, how do we know whether there's wraps or not, right? And the answer to that is that this is why we use phantoms. So that's why we have that whole spiel about using actual phantoms. We're in the process of actually making biomimicking phantoms, so we should know exactly what they should look like.
All right. I think there's a lot to discuss here, but we need to move on, unfortunately. Sure. Thank you very much. Let's thank our speaker again. All right, so our next and last speaker for this session is Jinwei He, who is an associate professor at George Mason University, and she's going to talk about revisiting mirrors for 3D imaging.
Thanks, Ioannis, for the introduction. I'm Jinwei from George Mason University. I'm very excited to give this talk here at ICCP, and thanks to the organizers for inviting me. I know our session is already over time, so I'll try to keep my talk short so you have more time for the coffee break. What I'm going to talk about today is how to use mirrors of being 2D, which is something you have probably heard many times in other talks. The easiest way to overcome this limitation is to use more cameras, which can give us more images from other viewpoints, and then you can run your favorite model view algorithm to recover 3D information. Instead of using more cameras, you can still do the same thing with one camera, but by using mirrors. Because mirrors can help you create images from new viewpoints, and this allows to estimate 3D using one camera in a snapshot way. In our everyday life, mirrors are used a lot to create new viewpoints that our eyes cannot directly see. For example, when you try on new clothes, you probably will use a mirror to look at the back of yourself. Dentists use mirrors to examine the back of your teeth, and when driving, we use mirrors in our car to look for traffic coming from from behind. In the research community, mirror-based imaging systems or chowdhury systems have been studied quite a lot. From Shi's early and very extensive work on chowdhury stereo to mirror-based light field that use mirror array to introduce horizontal and vertical parallax in a single image, and a kaleidoscope imaging system that use mirror chambers to create very rich and dense viewpoint variations. But all these systems have certain limitations, like some of them are 2.5D that only give us depths, not full 3D, and some may have too many views that occlude each other, and it is very expensive to segment and label these views. So in this talk, what I'm going to show you is the design space of mirrors for 3D imaging. Like how many mirrors do we need and how to configure these mirrors based on the need, with the goal to enhance the capacity of 3D imaging, but reduce the cost of computation needed for post-processing. All right, let's look at what does one mirror do, okay? So given a mirror, it creates a new image of the scene through reflection. And this is equivalent to have a virtual camera on the other side of the mirror. And if you think about the geometric transformation between the virtual camera and the real camera, it is essentially a combination of rigid transformation, which is in form of translation and rotation, and a flipping of the headness of camera coordinate system. And we want to represent it mathematically. This is the transformation matrix for a single mirror transformation. The rigid transformation that can be done by a single mirror is quite limited. This is because the translation and rotation, they're bonded together. For example, the virtual camera and the real camera, they must be symmetric about the mirrors that create this reflection. So in this case, if I want to map a camera to here, then its viewing direction is always along this way. You cannot map the camera to here, but with viewing direction that's upright. So what about using two mirrors? And by saying two mirrors, what I really mean is that I want to use them in pair. So which means that the two mirrors, they're facing each other and they relay the reflection without blocking each other's view. So under this setting, we can form the transformation matrix of this kind of like a paired mirror by multiplying the reflection matrix for each of them. And then the good thing about having a pair of mirror is now that we have higher degree of freedom for transforming the virtual camera, since now their translation and rotation becomes independent. And there's no flipping of the camera coordinate, since the camera coordinate has been flipped twice, and then it backs to what it is originally is. And this is a good thing for many post-processing algorithms, because you don't want to handle the flipping of the camera coordinate a lot of times. Now let's take a closer look at a property of the rotation for that mapping of virtual camera. And that property is actually very simple and nice. So for the rotation that can be created by a pair of mirror, the rotation axis is the cross product between the two normals of the mirror. And the rotation angle is twice of the angle between that two mirrors. So this here, you see the two normals, and this theta angle is the angle between them, which is the angle between the two mirrors, and then the rotation that can be created under this setting is twice of this angle theta. So now let's think about mirror design as a camera mapping problem. Say if we have a real viewing camera, and then how do we design the mirrors that a real camera look at in order to map the real camera to a certain view position that we wanted to map it to? So let's look at how to find out the mirror configuration. First, let's see how do we determine the mirror angle. So given the rotation matrices of the two cameras, this R matrix, we can find out their rotation axis and angle of rotation. With that, and with the rotation property we have just arrived, we can determine the mirror plane, which is a plane that is perpendicular to this rotation axis, and the angle between these two mirrors, which is half of the angle of that rotation we want. So if this 2 times theta, then the angle between the mirror, we call it theta, right? But since we only know the relative angle between these 2 mirrors, the mirror can still rotate in the space, but as a set. So now let's just pick a random angle alpha for the first mirror. We just fix the angle or orientation of one mirror. Then the orientation of the other mirror is simply alpha plus theta, which is the relative angle we have just derived. Although we have fixed the camera's orientation, they still have the freedom to move up and down along their normal directions, right? And so as the virtual camera that can be mapped. So this is what's happening for mirror 1, and then this is what's happening for mirror 2. And since the 2 mapped cameras, they're essentially the same virtual camera that is reflected by the first mirror, these 2 cameras, the mirrors mapped by the camera mapped by mirror 2 and the other camera mapped by mirror 1, they should coincide with each other. And with that, we intersect the trajectories of these 2 possible one-time reflection camera. And their intersection point is the virtual camera after the first mirror intersection. First mirror reflection. So with this first reflection camera, we then can determine the mirror location by perpendicularly bisecting the 2 camera baselines. One between this one and the real camera. So we have the location of mirror 1, and then we're bisecting the line between these 2 cameras, then we have the location of mirror 2. And with the real camera's field of view, we can further determine the minimal size of the 2 mirrors by only keeping the portion that can be seen by the camera. So with that, now I have a solution for the viewpoint mapping problem. Remember that our problem is that we want to map the real camera to a target viewpoint, which is this virtual camera. And then this mirror configuration can give us the exact mapping we want. And remember that this is under the assumption that we have this angle alpha for the first mirror, which is an angle we pick randomly. If we change this angle, we can still derive a viable solution in the same way, but mirrors will have different location and sizes. So this is what's happening. So with that design principle, we come up with a full surround 3D imaging system with paired mirrors. We use 8 pairs of mirrors and arrange them on a circle. And this is equivalent to map the real camera to a ring of virtual cameras that look at a scene from different angles. So we can tweak the angle between the 2 mirrors to change the viewing angle of the virtual camera. And the bigger that angle is, the lower the virtual camera is looking at, since it will go through a larger rotation. But this will allow us to have more side view coverage of scene, if you look at this too. So this one is more looking from the top, versus this one is more looking from the side. So after looking at this angle, let's look at how we pick the number of views. So these are some rendered images of examples of using different number of pairs, ranging from 4 pairs to 32 pairs. And you can see that the fewer the pairs or the virtual cameras, the less the overlap those neighboring views may have, right? Well, when you increase those views, although you have bigger overlap, but the angular coverage or the angular resolution of each camera is reduced. In the extreme case, you only have 1 pixel for a single camera. And then if the angular resolution is too small, you are not able to do the 3D reconstruction. And that turns the system into a multi-perspective imaging system. So we kind of like strike a sweet spot among these factors and pick these 8 views, such that we have enough overlap among neighboring views, and also we have enough angle coverage. So with that concept design, we made prototypes of the mirror system using 3D printing. So we first print out housing that determines the mirror angles and the separations, and then we put mirrors inside. So for imaging, we mount a camera on top of the system and look through the mirror and take model view images of the object that is on the other side, which is this guy here. So we also tried with mirrors with different angles, and here are 2 examples of them. And these are the images taken by these 2 prototypes. And we can see that all of them, they have 8 viewpoints because we have 8 pairs of mirrors. And the greater the relative angle between the 2 mirrors, the more side view we can see. And this is consistent with our earlier analysis. You may notice in this example here, the image quality is not that great. This is mainly because the mirrors we use are plastic ones and they may not be perfectly flat. So we ordered this kind of like a custom-built mirror lens that can be directly attached to the refractive lens for imaging. And since these are manufactured by professional lens makers and they use high-precision mirrors, so they don't have unwanted artifacts like a blurriness or aberration, the image quality is much higher. And since they're compact, we can use them for outdoor imaging. Now let's see the 3D reconstruction part. We choose to use the popular 3D Gaussian splatting for 3D reconstruction because this is a compact representation and also allow high quality novel view rendering. So in our algorithm, we first take images using our mirror system, and then we separate them into virtual view images with the calibration data of this virtual cameras. We can calculate an initial point cloud, and we also do visual Hall and derive depth constraint from that, and combine the virtual view with point cloud and depth constraint to give them as input to Gaussian splatting for the novel view synthesis. So I want to say that this is very challenging for regular Gaussian splatting because we only have 8 views, and the neighboring ones don't have that much overlap. So if you just run a vanilla Gaussian splatting, the results may not so good. And now let me just show you some results. So these are some rendered images we create because we then have the ground truth to compare with. Okay. So this guy is the vanilla Gaussian, and you may see some artifacts, some floating cloud on top of it. And we also compare with some algorithm that can handle sparse or few view input, but the results are still not so great. These are some other method. And these are some real data that we captured. Again, we compare with the algorithms that I showed you earlier. This is the vanilla Gaussian, and these 2 are the algorithm that can do less views. So this one is a berry that we capture from the outdoor using our portable lens. Since our solution is a snapshot solution, it can also do a dynamic capturing. It can handle dynamic scenes. And we took videos of objects that are dynamic changing. For example, this little plant that is budding. We take videos of it, and then we run our algorithm on each frame, and we can recover this 3D that is evolving over time. We also took this ladybug that is crawling. This is very challenging to capture with traditional approach because it's moving fast. But with our method, we can do the full surround 3D reconstruction of this kind of like a moving object. So in summary, what I want to show you is that mirror can help you to create new viewpoint, and I show you a principled mirror design for mapping camera from the real camera to the new viewpoint you want. And I showcase a full surround 3D imaging system that we built using such paired mirrors. And lastly, I want to thank my students and collaborators who contribute to this project, as well as NSF for funding us. So that's all for my talk, and I'm happy to take questions you have.
Thank you very much. So any questions? I'm actually curious, have you thought at all about whether curved mirrors would be useful for this? Give us different viewpoints, but some mirrors that can have either a conic shape, which is pretty well characterized, maybe either a freeform shape, that's probably really hard to fabricate, but in that case can give us very different ray spaces and very different ray samplings.
Right. So actually, I have a backup slide to tell you about this. So this is related to what I've shown you earlier about having more number of mirror views, and if you have infinite planar division, that is equivalent to have a curved mirror, right? So with a curved mirror, as I told you, because this division is very, very tiny, so basically your angular resolution is too small, and you cannot do 3D, but so we have another prototype which is made with curved mirror, and I can show you what the image looks like. So basically this gives you a multi-perspective image that people have modeled earlier. And with that, there's certainly opportunity for 3D imaging, and it can open up new possibilities for other imaging applications beyond 3D, because it is giving this continuous changing viewpoint.
So would using other continuous shapes, again I mentioned earlier, parabolas are pretty nice because they can focus at a specific point, or ellipses. Do you think that in those cases can give us some more general?
So these are actually circles. Yeah, these are circles.
Any other questions? I guess I have one more. If I'm designing a general kaleidoscopic system, can I try to automate this mirror design through some, I don't know, differentiable, some gradient descent approach? It seems like a very hard problem because it's not totally clear to me what kind of loss function I would use in this case. How exactly do I set up the merit function I'm optimizing? And also because the specular reflections themselves are a very discrete kind of event, right? So how would I go about automating a task of setting up an arbitrary configuration of, let's say, planar mirrors for a specific imaging scenario?
So this is a very interesting question. So since we have this tool, since I show you this tools for tweaking this mirror parameters given the need of imaging, it's if we have motor stage for holding these mirrors, it's actually we can actually do like the design. How do I put it? Learning learning on in the loop. A design of the system in the learning loop. Basically, based on the need, say if you want to look at specific points, then we can use that input to configure the mirror design and move the mirror to that certain direction. And if the algorithm is fast enough, that imaging process can be integrated in the learning process. And that imaging system design can further help with the learning algorithm.
All right, so let's thank our speaker again. I believe there is now a coffee break, and then we'll resume after that for a paper session.